Warning: hydrochloric acid and sodium hydroxide are corrosive and may release noxious acid and base fumes when heated. Cobalt compounds are toxic. Wear gloves and eye protection when handling them. Hi guys, here is MIH. A few months ago, I posted a video about extracting various lanthanide elements from a lighter flint rod. Following the project's big success, I tried to find other sources of lanthanides that I could try out, and I stumbled upon samarium-cobalt magnets. They are the first generation of ultra-strong rare earth magnets and got superseded by the well-known neodymium magnets later. The main reason I chose samarium-cobalt magnets over neodymium ones on this project is that around 70% of the samarium-cobalt magnet is cobalt, a very interesting element on its own, while most of the neodymium magnet consists of boring iron. Anyways, let's get started on the project. The basic plan is to dissolve the magnet in acid, selectively precipitate the lanthanides, and then separate the cobalt from other impurities. Here I have my samarium-cobalt magnet. It is in 10 smaller pieces and it has a dull gray color due to surface oxidation. However, it is notably more corrosion resistant than neodymium magnets, which are often coated in a layer of nickel for protection. I weighted the magnet, and its mass is 19.92 grams. I loaded the magnet into a conical flask, added around 150 ml of 30% acetic acid, and the color quickly turns pink. I then heated the flask on a hot plate to make the reaction go faster. I chose acetic acid because it was the only acid I had on hand, and also it makes the subsequent extraction steps a little bit easier. Looking back though, this decision was very, very bad. The dissolution of the magnet was extremely slow, and it took over 3 weeks to dissolve half of the magnet. As the acid gets closer to boiling, there was finally a visible reaction occurring. The magnet is releasing some bubbles, and the acid turns to a deeper orange-red color. The samarium and cobalt, as well as iron impurities in the magnet, are reacting with acetic acid to form the metal acetate and hydrogen gas. Over time, the acid slowly darkens in color, and the setting sun made its color much more beautiful. The camera certainly didn't do the reaction justice. The bright orange sunlight and the cherry red solution really made my day. After 4 hours of constant boiling and several additions of acetic acid, the mixture darkens to a purple-red color, but the magnet still didn't change in size and appearance, which was very disappointing. What is even worse is that when the solution cools, the reaction completely stops. I then came to my method of last resort, electrolysis. I set up a simple electrolytic cell with the magnet as the anode to try to make things go faster, and I ended up with this sludge of dark material after a day. I added back some water and was quite happy to see that the color of the solution darkened. It was 2 weeks later that I came back to the forgotten beaker with the acid and the magnet. The magnet did react with the acetic acid solution and loses around 8 grams of its weight in total, but I decided that I'm done with this. I quickly dug out my bottle of hydrochloric acid. It has an unknown concentration, but I assume it's around 20%. I poured out around 40 ml and directly threw the magnet in it. Unlike in the acetic acid, the magnet immediately produced a lot of bubbles, and upon heating, the dissolved cobalt formed tetrachlorocobaltate ions and gave the solution an intense blue-purple color. The acid soon boils, and the reaction went crazy and was way faster than the acetic acid. Meanwhile, I also put the acetic acid solution on the hot plate to dissolve the crystallized salts. When placing them side by side, the color comparison is quite striking. From this point on, there will be 2 different lines of experiment going on, so don't feel confused if I was frequently switching between acetic acid and hydrochloric acid. A few moments later, the acetate solution boiled, and I filtered it through some filter paper. Unlike the mixture before, the filtrate displayed a beautiful dark red color typical of cobalt ions. I quickly tested the pH of the solution, and it is around 4, which is exactly what I want. A major contaminant in our solution is iron, which exists as iron 3 ions. They start precipitating at a pH of 2, while our cobalt and samarium both precipitate around a pH of 7. The acetate ions in the solution have a buffer effect, which holds the pH of the solution around 4 to conveniently separate the ions. After around 3 hours of boiling, the reaction speed of the hydrochloric acid solution slows down a lot. I took it off the hot plate, and as it cools down, the blue color was taken over by the dark pink color of the cobalt ions. I then added around 14 grams of sodium bisulfate monohydrate. This has two purposes: to boost the solution's acidity and to introduce sodium and sulfate ions. Those ions are necessary in the lanthanide separation step later. I reboiled the solution and allowed it to react. Meanwhile, the acetate solution has finished filtering, and I can start the lanthanide separation step. As I just mentioned, the step requires sodium and sulfate ions, so I weighed out around 14 grams of anhydrous sodium sulfate, dissolved it in some hot water, and added it to the solution. Nothing apparently happened, but as I boiled the solution again, the solution became murky and some precipitates appeared. The light lanthanide ions, including samarium ions, react with sodium ions and sulfate ions to form an insoluble sulfate double salt. I then continued to boil down the solution to precipitate more of the double salt. However, a brown layer also appeared at the top, and that was certainly not the colorless double salt. I tested the brown stuff by dissolving it in some hydrochloric acid and adding some potassium thiocyanate. The intense blood red color indicates a large amount of iron present. I then added some paraffin oil to test for cobalt, and there was no apparent blue color in the oil layer, so little to no cobalt is present. Therefore, this brown stuff is iron hydroxide, and I can filter it off without worrying about losing my product. I did just that, and the filtrate is now pure cobalt and free of any metal ions except the sodium that I added before. I then weighed out around 10 grams of sodium hydroxide, dissolved it in water, and added it to the filtrate. A blue-black precipitate immediately appeared, which is pure cobalt hydroxide. Back to the hydrochloric acid solution. It has cooled down a bit and a lot of crystals appeared, which is hopefully our lanthanide double salt. I removed the magnet, filtered the solution, and washed the precipitate. I was happy to see that it is perfectly white and not pink. I tried to recover the samarium inside it, but unfortunately it didn't result in anything, so I discarded it. I then processed the filtrate just as above by adding 10 grams of sodium hydroxide in water, and the same blue-black cobalt hydroxide precipitate appeared. I combined both portions of the mixture, filtered them, and washed the precipitate. And this is the final yield of wet cobalt hydroxide from the acetate and chloride portions, which represents around 12 grams or 60% of the magnet's weight. I then added 150 milliliters of hydrochloric acid to redissolve all this precipitate into cobalt chloride, which I can then recrystallize. Unfortunately, after the two acid dissolutions, there are still 8 grams of the magnet left undissolved, so I quickly made some hydrochloric acid and added 40 ml of it to the magnet. The reaction looks exactly the same as before, so I won't bother you with the details. All you need to know is that even after this, 4 grams of the magnet is still not reacting, so I gave up and stored it. I'm really tired by this point and didn't bother to remove the lanthanides from the solution, so I directly combined it with the rest of the cobalt chloride solution. Upon boiling it, all of the cobalt hydroxide dissolved, forming a dark red solution. The solution is then poured into a large crystallizing dish and evaporated. After an hour and a half, the solution turns to the familiar deep blue and its volume decreased by a lot. I removed it from heat and allowed it to crystallize. When the dish cooled, a large cake of nearly black crystals is formed. I decanted the dark blue supernatant and added some water to the crystals to wash them. Surprisingly, the crystals instantly turned pink when they touched the water, and I was really happy to see my product appearing. I then decanted the supernatant and allowed the crystals to dry in air. I came back to my crystals 1 week later, and all of the water evaporated. I added some water and filtered the mixture to remove the impurities. I washed the crystals once with water and once with ethanol, and transferred them to a hot plate to dry. As the crystals lose water, their color slowly changes from pink to green, and then a dirt yellow, and finally gray. After no water vapor was seen to be given off, I bottled my product, which has a slightly pink tint in its grayness and weighs 6.89 grams. However, real anhydrous cobalt chloride has a vibrant blue color instead of the gray color here, so there must be still some water not removed. I did some research and found out that the first 5 water molecules are relatively easy to kick off, but the last one really requires some strong heating that my hot plate cannot reach. I added a small sample of my product in a crucible and heated it with my blowtorch. The color darkens significantly and turns to a blue-black color. I then processed all of my products this way. Upon comparing the two samples, you can clearly see their color difference. The fully dehydrated product weighs 5.88 grams, which means that we've lost about 1 gram of water. This is around 14.5% of the sample's original weight, and if we substitute the formula of cobalt chloride monohydrate in the equation, it fits quite well. Just to really make sure this black powder is actually cobalt chloride, I dissolved a pinch of it in water and immediately gave the vibrant red-orange color of cobalt ions. Apart from the abnormal color of my cobalt chloride product, I also noticed a few weird phenomena when dealing with the mother liquor from the crystals. When I boiled it down, the solution displayed such a dark green color that I mistaken it for a concentrated copper chloride solution. I then tried to add some water back in it, and all of a sudden, the solution reverts to the normal pink color, which was really surprising. In conclusion, this project of extracting cobalt from samarium-cobalt magnets worked to some extent. It wasn't a perfect success because I designed the procedure somewhat badly and many unexpected things happened, but the project really improved my understanding of the general procedures of metallurgy and metal extraction. See you next time.